Hello there. So our learning query for today is how we can use differentiation to help us solve complex equations. You've already looked at some numerical methods for solving equations. We're now going to look at another one, but this involves using our differentiation skills. And this is called the Newton-Raphson process. So we've already looked at working out approximate solutions. Sometimes we'll come up with equations that we can't solve using methods that we already know. Lots of the maths that you've already looked at, the questions are carefully picked to be a different type. They might be linear equations, which we can rearrange to solve. They might be quadratic equations, or they might have exponentials or logarithms involved. And we've got strategies to deal with lots of these things, but we might not always be able to deal with the type of equation thrown at us. So in those situations, it's useful to have something like a numerical method to give us a different approach that may work. You should have already seen a change of sign method and an iteration method. These are covered both at GCSE, more detail and with more difficult functions in Year 13 maths. The Newton-Raphson process is another numerical method for solving equations using our differentiation skills to help. So this is just a quick demo of how it works. So we've got a function sketched out with the blue curve. It's got a solution or a root when it equals 0, marked on here with alpha. So similar to iterations, we start off with an initial approximation. So this has been marked as x0. And what we consider is a tangent to the curve using this x value. And if you actually follow the tangent down, have a look, where the tangent then meets the x-axis, in this case, is giving us a better approximation to the root. So the tangent has brought us nearer to the root. So we're then going to use this x value where the tangent meets as our next x value, consider a tangent to the curve at that point, and that brings us even closer down to the root that we're looking for. And we could repeat and repeat and repeat like we do with iterations to get closer and closer and closer. But how are we going to turn that into a piece of math? So we can derive a formula to help us do this. If we consider our first x value meets the curve at this point, that would be our tangent line. That gives us our second x value. So considering the green triangle there are two different ways we can calculate the gradient of the tangent which links to that green triangle. So the first way is we could do it using calculus. So the gradient of that red tangent line could be worked out by differentiating f of x. So that would be noted as f dashed. And because it's the tangent using the x0 value, we could do it as f dashed of x0. We'd substitute that number in. The other way we can work out the gradient is doing our usual change in y over change in x. So the change in y, the y value at the top up here would just be f of x0, and the y value down here would actually be 0. So this height, change in y going up here, is just going to be f of x0. The change in x, the horizontal change between these two, is going to be the difference between the two x values. So this would be x0 minus x1. So this is two different ways of working out that same gradient. One of them is by considering differentiation. The other one is just your standard gradient formula. We could do the same thing if we consider the next x values. So if we consider the next tangent along, and we consider this yellow triangle, so the same thing with this one. So the gradient from differentiation this time would be f dashed of x1. Okay. And then if we considered it by doing it as a regular gradient, the change in y, so our y value up here would be f of x1. And that's a change between that and 0, so that would be the change in y. The change in x is going to be x1 minus x2. So we've done it for two specific cases, for the first triangle and for the second one. If we considered it generally, so if we decided to do this generally, we want to consider xn, the nth x value. So I'm going to use, if we use this as f of xn, so this is every time I've got a 0 or a 1, that's my lower x value, so this would be f of xn. So I'd have to do xn minus xn plus 1, that would be the next one along in order. We had 0 here, and then 1 in the first formula, we then had x1 and x2 in the second formula, so xn and xn plus 1 makes sense for the third formula. And we're actually going to use a rearrangement of this to consider how we can work out x of n plus 1. So if we put a couple of steps of rearranging in, so if we multiply up by xn minus xn plus 1, that will give me f dashed of xn multiplied by xn minus xn plus 1 would be f of xn. If we expand out the brackets, we'd get f dashed of xn times by xn minus f dashed of xn times by xn plus 1. That would have to be f of n, and we're trying to make the xn plus 1 the subject of our formula. Because it's minus at the moment, I'm tempted to rearrange that onto the other side of the equation. So I'm going to make it f dashed of xn times by xn minus f of xn equals f dashed of xn plus 1. And we're going to divide through by f dashed of xn to get us a formula for xn plus 1. So xn plus 1 is going to be f dashed of xn multiplied by xn minus f of xn all divided by f dashed of xn. And we can actually do a bit of simplification because we've got f dashed of xn in the first term on the top and on the bottom line. So we'll cancel down in that first term. So that's just going to leave with xn minus f of xn over f dashed of xn. So we can work out this improved estimation using our starting x value and then subtracting what we get when we do the difference between f of xn over f dashed of xn. So this is what that formula looks like in our formula booklet. We've got to set our equation up to make sure that it's f of x equals 0 because we're considering when it crosses the axis line. In our setup for the derivation of it, we've got xn plus 1 equals xn minus f of xn over f dashed of xn, so that's the same as what we've come up with. And it's given in the formula book, you don't need to memorize it, we just need to look it up and use it when we're asked it. So this is an animation from Wikipedia just showing you how this formula can run through. This is quite a slow to converge function. It needs quite a few repeated steps, but eventually with the 5th repeat gets us quite close to the solution. So you should be able to notice each time it gets slightly closer and slightly closer again to the solution. So if we run through a quick example how we're actually going to use this. So we've got our formula given that we can look up, we've been asked to use the Newton-Raphson process to find the root of a quartic equation. We've been told it's near to x equals 3, so that's our starting value, and we want the answer correct to 2 decimal places. So the first thing we want to consider setting up, we need to set it up in this f of x notation. And we need it to equal 0, so we're going to have to slightly rearrange the starting equation. So x to the power 4 plus x squared, and we're going to have to minus 80 to make sure it's set up as equaling 0. Okay, also for part of our formula, we need to differentiate. So we need to work out f dashed of x, because we're going to have to use that as well. So if we're going to work out f dashed of x, we need to remember our differentiation skills. So x to the power 4 will become 4x cubed. X squared is going to become 2x. And if we differentiate minus 80, that would reduce to 0. So now we've got our two different bits, we can start working things through. So we're going to use the first x value as being 3. So if we use x0 as 3, so to work out x1, we need to substitute this x0 value in. So it's going to end up being 3 minus, we need to do f of 3 over f dashed 3. So we're going to substitute 3 into the f of x equation and work out our value. We can substitute 3 into the f dashed of x equation and work out our value. The easiest option actually for this is to use the answer button on your calculator. So here's a quick demo of how we can type that in. So if we'd like to set this problem on our calculator, the first job is I'm entering 3 and then pressing equals. That saves the initial value as my first one. Now that's in as the answer function. So I can now use the answer button to repeat the calculation over and over again. So I want to do 3, so my answer minus, so on the top line I need the function, so I need answer to the power of 4 plus my answer squared, and then minus the 80. On the bottom line, we need f dashed of the value substituting in. So I need 4, and then I need my answer cubed plus 2 lots of my answer. So we've put in the initial value, we've used that as 3, we then use the answer button to replace every time I would like to put an x into any of the functions. So that's given my first value out of 166 over 57. The question talks about decimal places, so if we use the S to D button to switch to decimals, that is giving me 2.91. And now all I need to do is keep pressing equals to keep repeating that process. So now I've got this first value. Okay, I can repeat the same process again, and because I've set my calculator up in this way, all I would need to do next time is press equals. The calculation that's actually going to be going on in the background is 2.912 minus f of 2.912 over f dashed of 2.912. So all of that's going to be going on in the background. All we need to do on the calculator is press equals again, which gives me 2.908. And actually, we've been asked for an answer to 2 decimal places. The first answer we've got here to 2dp gives us 2.91. And this one here, rounding it to 2dp, would also give us 2.91. So we can be confident that to 2 decimal places, our answer is going to be 2.91 because we've had 2 answers in a row that both round to give the same thing. If they rounded to give something slightly different, we have to repeat again. Okay, so our final answer that we're going to settle on is going to be that x is approximately equal to 2.91. Okay, to 2 decimal places. So we've got another similar problem here set up. You may want to pause the video and have a go for yourself first, and then check when we run through the question to make sure that you know how to answer. Part A is going back to a method that we've already looked at, which is your change of sign method. You've been asked to show the equation as a root in the interval where x is in between 1 and 2. So again, for a root, we're considering roots, it's when the function equals 0. So we're going to substitute in f of 1. So if we substitute it, we'll end up with 1 cubed plus 2 lots of 1 squared minus 5 times 1 minus 4. If we calculate a value for that, let's see what we come out with. So that gives us negative 6. So if we're expecting it to be a change of sign method, we would expect f of 2 to give us a positive value. And this change between positive and negative must mean it was 0 somewhere in between. So f of 2 would be 2 cubed plus 2 lots of 2 squared minus 5 times 2 minus the 4 this time. So that is coming out as being 2. Okay, so we could then make a conclusion that there is a change of sign we can use our 3 dot symbol, therefore a root in the interval where x is in between 1 and 2. Okay, so part B, back to our Newton-Raphson methods. We've been asked to use 2 as the first approximation. If we look at the two answers we got from the change of sign rule, we got a value of 2 for f of 2 and negative 6 for f of 1, so 2 looks to be a little bit closer. We can't know for sure because of the full nature of the function, but that's probably going to start us off a bit closer to the solution. And we're going to have to differentiate before we're able to use that. So first job is going to be to work at f dashed of x. So f dashed of x is going to be 3x squared. Differentiating the 2x squared is going to give us plus 4x. And then the minus 5x will simply be minus 5, and the minus 4 will go to 0. So we've now got our f dashed x function. So we've been asked to use a starting value of 2, so our x0 value is going to be 2, and we can use the trick with the answer button on the calculator again to help get a solution. We've been asked to get an answer correct at 3 decimal places this time, so more accurate than before. So we may need to repeat more times. It all depends on how quickly our process converges. So we're going to work at x1. And to do that, that's going to end up being 2 minus, so we need to do f of 2 over f dashed of 2. And we'll substitute that all in on the calculator, use the answer button to make it quick and easy to do. So x1, I'm coming out with a value of 1.86 recurring actually. And then because we've set it up like this, so to work x2, I can just press equals again on the calculator. And this is giving me this time 1.8558. So we've been asked to go for 3 decimal places, so we're not quite there yet. So if I work at x3, I'm coming out with 1.8557. So actually now these two are the same thing to 3 decimal places. This would round to be 1.856 and x3 would also round to 1.856. So we can go for our approximation for x. We'll go for 1.856 to 3 decimal places. So that's our approximate solution for x. The Newton-Raphson method isn't perfect. There are instances when it will fail. So one that should be fairly obvious was if the first approximation we use actually hits a stationary point, we end up with a slightly odd situation where the tangent will never meet the axis. Our gradient comes out to being 0. So if you think about it from the formula's point of view, we'd end up with a divide by 0 in the formula, which would make sure that didn't work out. And actually, the way we've set it up graphically, it wouldn't work because we'd never get this triangle shape we could work the gradient out for. So it would never meet the axis somewhere new. So that's one instance where it won't work. The other time as well is the ones we've looked at converge towards an answer. They get closer and closer to the solution we want. But if a particular function is set up in a certain way, it may be that actually our answer diverges and gets further away from the point we're interested in rather than closer to it. So if you just take a quick look at the example down here, if we start with our value here, our tangent actually takes us over here, and then the tangent from there takes us over here. And then we'd be back up on the curve up here somewhere, and that would take us even further away. If we followed that tangent line on somewhere in that direction, we'd be even further away from the route we wanted. So sometimes our formula may set up just because of the nature of the shape of the function won't actually take us where we want it to. With this function, we may be able to get it to work if our initial approximation was closer to where we wanted it to be. We might find that we can get it to work out, but we'd have to run that through and see exactly where that ended up. Okay, so just to finish off, if we go back to consider our learning inquiry, so we're considering how we could use differentiation to help us solve complex equations. So you should be able to explain how we can use these two forms of gradient and then rearranging from that to consider a repeating process to get closer and closer. Again, similar to what we've done in earlier topics, why is it important to have a numerical method to give us approximate solutions? So some functions are just quite difficult to solve using other methods. So it's quite nice to have this numerical way of coming out with a solution. Again, lots of calculators have a solver function, and they will use a numerical technique to come up with an approximate solution to it. Again, they can repeat processes very quickly and come with very good approximations. Limitations of Newton-Raphson, we've talked about two of them already. There's another one that you might have thought of. We need to be able to differentiate to use Newton-Raphson. So if the function that we're trying to solve, we don't know how to differentiate, we'd then have another issue in there as well, that we couldn't use this method and would possibly have to use a different numerical method to solve the problem. Okay, thank you for listening. Please make sure you complete any follow-up tasks set by your teacher.